Next, we'll talk about how we recognize alternative optima and how we find them using the simplex method. First, let's consider the example that we solved graphically and using the simplex method before. This is our heavenly pouch example, so we saw that this problem had a unique optimal solution at the point C. Graphically, how do we know it's unique? Because we see that when we draw the isoprofit line and we move this line towards the increase in the objective, the last point that we are going to touch in the feasible region on the way out will be the point C, and this is the only point that we touch at this profit level within the feasible region. So once we increase, the profit will be out, so that's why it's the optimal point, and because it's the only point that corresponds to this level of profit, this is a unique optimal solution. Now let's look at the simplex solution. So this is the optimal tableau for this problem, and let's write the objective as the expression of the decision variables for this optimal tableau. So we have z is given by 9,375 minus 25 fourth S2 minus 15 fourth S3. And obviously objective is expressed through the non-basic variables only, meaning that the coefficients for all the basic variables are zeros, as always in the basic feasible solutions. Looking at this expression, we can see that because the coefficient for both S2 and S3 is negative, once we change S2 or S3 from 0 to something else, the objective function value will decrease and the solution is not going to be optimal anymore. And remember that S2 and S3 are non-negative, so the only way we can change the values for these variables would be to a positive value, and as a result, the objective is going to drop. So to obtain an alternative optimal solution, if one exists, we would need to modify the value of a variable that has a zero coefficient in the objective. All non-basic variables have negative coefficients, which correspond to positive in the tableau form, and the only variables that have zero coefficient in the objective would be the basic variables, right? But then setting S2 and S3 to 0 uniquely define the values of the basic variables. If you want to change the value of a basic variable, we would have to modify the value of at least one of the non-basic variables, because otherwise you would violate the constraints. So therefore, whenever I have all non-basic variables with positive entries in row 0 of the optimal tableau, this guarantees that the optimal solution is unique. All right. And the only possibility for an alternative optimal solution that we can have is when at least one of the row 0 coefficients for non-basic variables would be 0. So let's consider this possibility. For this purpose, we are going to look at a modified heavenly pouch example that we first looked at when we were discussing the graphical solutions of two variable LPs, and we were demonstrating an example of a problem with infinitely many optima. In this case, we modified the objective of the original heavenly pouch problem by changing the coefficient for x1 from 15 to 20, and then we can see that the isoprofit line is parallel to the third constraint here, and therefore when we keep increasing the level of profit, we will hit two corners on the way out of the feasible region, and as a result, both x star and x prime are optimal solutions, and everything in between is also optimal. All right, and we can see that if we look at the optimal tableau for this scenario, then there is a zero coefficient for one of the non-basic variables. More specifically, the row 0 entry for S2 is equal to 0. And when you have a situation like this, then this is a sign that there is a potential for alternative optimal solutions. Because now the coefficient for S2 in the objective is 0, and by altering S2, I'm not going to change the objective value. But obviously, when I increase S2 from 0 to something positive, the actual solution will be different even though the objective is the same. And this is exactly when we have an alternative optimum. We can see that if you look at the potential for increase of S2 in this tableau by looking at the ratio test, we see that the ratio test would allow a positive increase in the value of S2, and if you perform the simplex step by using S2 as the entering variable, then we would end up in the point x prime. So I suggest you do it as an exercise. Do the pivot of the simplex method by using S2 as the entering variable, and then show that you will end up at the point x prime as a result, and you will obtain an alternative optimal solution. So whenever we have a zero coefficient in row 0 for a non-basic variable, this is a sign that there potentially may be an alternative optimal solution. It doesn't guarantee that there will be an alternative optimal solution, because there is a possibility that if, let's say, you have by 0 right-hand side and the positive entry in this column, then we have the degeneracy and we are gonna end up at the same solution even when we try to use S2 as the entering variable. But if the ratio test yields a positive value, then you'll obtain an alternative optimal solution. Here is another example to look at. We have an optimal tableau here because we can see that entries in row 0 are all non-negative, and we have a non-basic variable x2 that has a 0 coefficient in row 0. Alright, so if you use x2 as the entering variable, again, we see that we are gonna end up at an alternative optimal solution, because if we perform the ratio test, then what is gonna happen, these two rows don't participate. From this row we have the maximum increase of 8/5, and from the last row we have 5. This row is going to win the ratio test. This will be our pivot element, and we can see that after we perform the iteration, the value of x2 which enters the basis is going to be 8/5 instead of 0, but the objective is not going to change because the coefficient for x2 in row 0 is 0, and as a result we are going to obtain an alternative optimal solution. Please complete this step to verify.
Yes. Remember the homework, y'all.
And then from there you build on top of that. But if you're lazy, man, I don't want to talk to you. I want to deal with you. You're going to make me feel dumber.
Next we'll do some proving, and we'll show that whenever we have alternative optimal solutions, there will be infinitely many of them. Alright, so you can have a unique optimal solution, but then once you have more than one, you cannot have just 2 or 3. Once you have more than one, you have infinitely many of them, and they will form a convex set. We saw this geometrically before. Say here we had the x star and x prime were alternative optima, and everything in between was also optimal. So once you have 2, you have infinitely many, and now we are going to establish it algebraically. So assume that you have 2 optimal solutions, x star and x prime are alternative optima, and assume that the problem we are dealing with is maximize C transposed x such that ax is equal to b, x is greater than or equal to 0. This is LP in the standard form. Then what we are going to show is that if you have these 2 optimal solutions, then every point in the convex combination of these 2 solutions will also be an optimal solution. So let's consider an arbitrary convex combination. Let's call it y, and it's going to be given by alpha x star plus 1 minus alpha x prime. And then what we need to show is that the objective at the point y is exactly the same as at x star and x prime. So for that we'll just take C transposed y, and then we'll substitute for y this expression alpha x star plus 1 minus alpha x prime. This is the same as alpha C transposed times x star plus 1 minus alpha C transposed times x prime. And this is going to be given by z star, our optimal objective value. And this is also going to be given by z star, because remember, both x star and x prime are optimal solutions. So at both of these points, the objective is equal to z star, which is the optimal objective value. So as a result, we'll have alpha plus 1 minus alpha z star, which is exactly z star. So we see that the objective value at the point y is exactly the same as in x star and x prime. Now the last thing we need to prove in order to show that y is optimal for our problem, we need to establish the feasibility of y. In other words, we need to show that ay is equal to b, and then y is greater than or equal to 0. We have previously shown that this set here is convex, and this means that any convex combination of the 2 points from the set will also belong to the set. Therefore, we can claim the feasibility of y based on the convexity of the feasible set for our problem, which we already established before.